thanks a lot to the primary organizers for the invitation to speak here, and thanks to everybody who's still here at this time. I know it's been a very long day that people have had. So I will talk about this paper that came out last month. And it is a bit of a long paper, and there's a lot of technical parts to it, so I thought maybe if I give the talk on the whiteboard, I will be kind of forced to just focus on the main idea of what we did, and not so much on how we did it, which is what I would probably be more focusing on if I was giving a slide talk. So let's try to just give you a little bit of a feeling of what the problem is and what we are trying to achieve. Okay, so this. Before I go into the N=2 theories, let me just start with something that you might at some point have been familiar with or seen, even though I know that it's not directly in line with many of the other talks in this workshop, which has to do with integrability in the N=4 planar superior Mills theory. Now, what is this theory? It is a theory of a vector multiplet and 3 kernel multiplets. And it was realized that back in 2002 by Minahan and Jarenbo, that, building on earlier work, of course, that if you want to study the spectral problem of this theory in the planar limit, then, and by spectral problem I mean to find if I give you an operator at some point x, which is given due to gauge invariance, and I'll be focusing on operators built up from the scalar fields. So you have some operator x, y, x, z, and so on. What you want to know is the spectrum of the theory, meaning that what is the eigenvalue of the dilatation operator of this theory. The dilatation operator, because this is a superconformal field theory, it's part of the superconformal algebra, and you want to diagonalize the dilatation theory. And what Minahan and Jarenbo realized is that this problem can be mapped to that of a specific spin chain. So you don't have a trace, but you impose simplicity. And okay, let's for simplicity also be in some sector where I only look at some SU2 sector where you only have x's and y's. You can replace these by spins, so up, down, up, and so on. And the dilatation operator becomes the Hamiltonian of an XXX Heisenberg spin chain at the one loop level. So if at one loop you want to find the spectrum of this theory, so what are all the gauge invariant operators and what are the dimensions, it's a very complicated a priori diagonalization problem, but you can simplify it by using this analogous prescription of a spin chain and knowing this Hamiltonian, and then using techniques that were invented already in the 1930s by Bethe for the Heisenberg chain, and then generalize those to the more complicated cases that you would get if you go to higher loops, if you include not just SU2 but SU3 or more operators, and so on. So that's the theory that is kind of pretty well understood by now. Okay, so there's been a lot of work over the past 20 years on understanding the spectrum and going even beyond to correlation functions and things like that. So our original motivation is comes from this, so from understanding the understanding of integrability and how important that has been for this theory. But now we want to look at what happens if you reduce the supersymmetry. And one way of reducing the supersymmetry is to do an orbifold projection. So you can reduce it by taking these fields and identify them like this. So this is a Z2 that I'm doing here, and at the same time taking all the fields, let's phi is any of these fields, to some tau, phi, tau minus 1, where tau is this. Okay, so this is a 2n by 2n, so these are n by n, and you start with gauge group SU2n. So basically you start with some matrices which are 2n by 2n, and you perform this identification. What you get is that, well, you get a theory which is n equals 2 rather than n equals 4. And and for later use, I'm going to write down just very quickly the spectrum of the theory, and well, not the spectrum, sorry, the fields of the theory. So basically, this V is not going to play much role in this talk, but X.
Sorry?
Yes.
Tau looks like the identity matrix.
Excuse
Tau
me?
looks like the identity matrix. What?
Oh, sorry, there was a minus here.
Okay.
Oh,
Okay, it's not clear.
yeah, sorry. Okay, so what happens if you do this? What stays behind and is invariant of this orbifold projection is two fields which are bifundamental, and one field which is still adjoint of the two. I'm going a bit quickly because I assume this is somehow familiar, but otherwise please ask and I'll explain in more detail. And what also happens, of course, that this SU2n is reduced to SUn times SUn. So there's two gauge groups, SUn1 and SUn2. They're the same, they can be exchanged, but for concreteness, I'm writing here the fields as they transform under the first and the second. So these are bifundamental, meaning that they're transforming the fundamental of the first and the anti-fundamental of the second, while these are adjoints in each individual SU.
So n equals 4 has 6 scalars, right?
Yes, so here I'm really focusing on the holomorphic sector, so these are the chiral multiplets.
I see.
In everything I'll be saying, there's also the conjugate fields. They're going to play a big role, but I've chosen not to emphasize them too much in this talk. But a big part of our paper was understanding all the aspects of the non-holomorphic fields as well, the mixed sectors and all that.
So are these the scalars of the multiplets? Like this is the entire multiplet having the orbifold?
Sorry?
The orbifold is happening on the entire multiplet or only the scalar sector?
Only on the scalar sector. So you can think of this as if you think of a D-brane setup, right? So you have some D3 branes with a target space which is a C3, six-dimensional target space. So these are the two components of the C3. So basically you're taking a C2 mod Z2 times a C1. So this one is the one that stays unchanged. If I was orbifolding all three, I would be getting an n equals 1 theory. That's also very relevant and important, but okay, we're focusing on n equals 2 just for simplicity, essentially. Right. So that's the theory, and as many of you know, these kinds of theories are convenient to describe in terms of a quiver. So you can think of the two nodes, 1 and 2, and you can think of the fields as going between these nodes, like this, and like this. So that's the quiver diagram for this particular n equals 2 orbifold theory, where this is Z1, this is Z2, this is, let's say, X12, this is Y, or the X21, Y12, and Y21. So the big difference now compared to the n equals 4 case is that when you try to create gauge invariant operators, since some of these fields change the gauge group, right? So this goes from gauge group 1 to gauge group 2. You have to combine them if you want to write something gauge invariant and close the trace and all that. You have to combine them only in specific ways, right? So for instance, if you have, suppose I want to make a trace in the first gauge group, maybe I start with a Z1. That can only be followed by X12 or a Y12. So I can write, let's say, the Y12 here. This can only be followed by something which starts with a 2. So maybe it's a Z2. Or maybe then there will be an X21, and so on. And the final field also has to have an index 1 if I want this to be a trace. So let's say X21 again, okay, after something. Okay, so this is the main difference essentially, and that's what we're kind of trying to understand in some sense a bit better. how this restriction by basically being able to contract the gauge indices, how does that affect, in particular in this case, the symmetry of the problem, as I will explain. Now, these theories, of course, have been well studied. And our motivation for all of this is a paper by Abhijit and Ellie and Leonardo they had a series of papers, but there was in particular one from 2010, where they look at this particular theory from various perspectives, but in particular from the perspective of integrability. So they were looking at equivalent problems to this problem, and looking at considering this as a magnum in the corresponding spin chain, and studying those kinds of problems. And it's also been studied earlier at the orbifold point, which I will explain now, by Beisert and Royman and so on. So there are two kinds of theories you can think of here. First of all, when you just take the orbifold, the coupling corresponding to this gauge group and the coupling corresponding to this gauge group are the same. That's how it naturally comes out when you take the orbifold. However, without breaking n equals 2 superconformal invariance, you can individually modify these two couplings. So this can become a G1 and this can become a G2. Later in the paper, I'll be using notation, which is also from that paper, that I'll be using kappa for the ratio, because you can kind of normalize the couplings away, and then there's only the ratio of the couplings that is relevant.
Just one question. If we write down the action, say F mu F mu, how do we construct it as a trace for this theory?
So, well, the gauge fields are still adjoint, so there's no difference for the gauge fields.
But there are two of them, right?
Yeah, you just add.
Just add them.
Yeah, so they're two independent gauge groups.
Yeah.
The problems start when you want to write, well, the problems, but things become more complicated for the scalars. So, for instance, in superspace, because I will mostly be using superspace language. For instance, your kinetic terms are going to be of the type, let's say, x bar 1, 2, e to the minus g2 v2, x 2, 1, e to the g1 v1. So you see that now you get kinetic terms which depend on both gauge fields. But expanded out, you get the correct. If you expand this into components, you're going to get all the correct covariant derivatives with either A1 or A2, depending. You're going to get some kind of commutators.
Yeah. And another question is, in certain limit, we can decouple one from the other, right?
I mean, you can take the limit, which I think that was also one of the primary motivations for.
Does that become n equal to 1 instead of?
Well, you can take one of the limits, one of the couplings to 0.
Yeah.
That makes that SUN global. So then you get something like superconformal QCD. So you have a flavor group. You gain a flavor group.
Yeah.
And there's many interesting aspects there. But from our current perspective, that's not the limit that we care about. We care about a small deformation away from the orbifold point, not going all the way to 0. The problem there is that the spin chain picture kind of breaks down a little bit, because now you have like global. So basically the trace splits into smaller traces, and it's a bit difficult to make much sense of it as a planar theory with magnons moving on a spin chain. All right, so that's the idea, and maybe I should also write. Okay, I think maybe I'll be focusing mostly on the superpotentials. But okay, so the main statement here was that if studying magnum scattering, it turned out that these theories are not integral. Or at least, let me say, that the standard way of finding integrability using the Yang-Baxter equation did not apply. The Yang-Baxter equation did not hold in those, for the marginal deformed theory where G1 is not equal to G2. At the orbifold point, these theories are fully integrable and more or less exactly the same as n equals 4. There's just some phase factoring to add to your Bethe answers, but everything more or less works through. But the moment you make these couplings different, then you definitely lose the Yang-Baxter equation.
Sorry, Costas, what is the beta inserts in this case, particular case? What's the statement?
Okay, so normally the tangents works with, when you have these, so you have some magnons, right? With, let's say, P1, P2, P3. And when they cross each other, you have an S matrix. Right, so the problem is that, okay, so maybe just as an example here, what happens is, let's say this is an x12, this is an x21, this is an x12. In this sector, which is only made up of x's and y's, as you can see, what you get is an alternation, which might remind some people of the BJM theory, but it's not exactly that. This is a one loop, not two loops, as in the BJM. But there are quite some similarities to the BJM. But this is an alternating chain where, and this you can really see that the Hamiltonian acting on these two is the Heisenberg Hamiltonian with a kappa, while acting on these two, it's the Heisenberg Hamiltonian with a 1 over kappa. And then it alternates kappa, 1 over kappa. So that's the spin chain picture. So this is an alternating chain, Heisenberg chain, but with alternating couplings. It's something that people have been studying sometimes in condensed matter, but also explicitly. There are realizations of these as actual molecules that people have studied. But integrability, even for this very simple system, just Heisenberg chain, is not known. They are not thought of as being integrable. Okay? So, and the way to see it is, well, if you have 3 magnons, then you find the S matrix for 2 magnons, and then you check that, is there some version of the Yang-Baxter equation for the S matrices? So normally you'd expect something like this, but this does not hold. Okay. And technically, I mean, it's kind of simple to see. Well, okay, if you know this work, it's very simple to see because they calculated the S matrices, and they found that it doesn't, the Yang-Baxter equation is nonsense.
So every integrable system is given by Yang-Baxter equation?
Well, see, that's actually our motivation for this. There are generalizations of the Yang-Baxter equation, the standard Yang-Baxter equation.
Okay.
So, in particular, there's something known as the dynamical Yang-Baxter equation, which it is where it is possible, which is still integrable, and we are still hoping that such simple chains can go under the framework of the dynamical Yang-Baxter. So in a previous work, also with Elni, we showed that you can get something known as an alternating XX model. But that's kind of a free fermionic model, and it's kind of trivially integrable in a sense. We have not been able to find an alternating XXX model, but that's something which is unrelated to today's talk, because I'm not going to mention integrability again today. But it is something that we're working on. So there is still some hope that integrability will present itself in some slightly more complicated way than standard Yang-Baxter. But even if not, what I'm hoping to argue is that these theories are still interesting. They still have a lot of symmetry, and it can be used for perhaps other things beyond just integrability. I mean, integrability is great to have. I mean, you get a lot of power, but there's other things that you might also want to have, which have not been explored. Okay, and that's going to be the focus.
Costas, after some years after this paper, with Leonardo, I had written this paper called Twisted Magnons,
Yes.
which is a different kind of deformation of the symmetries was used to fix the spectrum to all.
Yeah, but you're looking but there you're looking at the SQ2 sectors. Yeah, and then you were doing it even at all loops, right? You were able to kind of fix it. Yeah. No, but
I was
here,
wondering whether the fact that there is some sort of a symmetry deformation exists there, does perhaps that suggest that there could be a deformation of the Yang-Baxter equation?
yes. I mean, I think all these papers are, very motivational for us in order to, hold out some hope that there is much more to the story than we can see. Okay, but from the current perspective, maybe there's one more thing that one needs to write down just to clarify the structure, which is that if you take n equals 4, I don't want to write down a lot of complicated potentials and stuff, but at least the superpotential is this, and in the n equals 2 case, what happens is that you now have two traces. Trace 1, I think I'm making some space. Of x1, 2, y2, 1. So remember now there are 6 fields. I'm working in the kind of picture where I'm focusing on these fields rather than the full picture, because that's what makes sense if you want to deform, marginally deform. So you get this minus y, 1, 2, x, 2, 1, z1 plus trace 2, and then kind of the opposite. So this would be now an x2, 1, y1, 2, minus y2, 1, x1, 2, z2. And at the orbifold point, these have the same coupling, G and G. And if you marginally deform, then the coupling changes according to what the Z field is. So the actual potential that we are eventually going to be interested in has two different couplings, G1 and G2. Okay, so that's a generalization from just a very symmetric n equals 4 point to this n equals 2 symmetric.
Hey, what do you mean the coupling depends on the field is diameter, right?
So what I mean is that it's just a quick way of remembering how the couplings go. That's so to get this. The superpotential is basically okay because of n equals 2 supersymmetry, right? This is in the same multiplet still as the vector field.
Okay.
So when you are changing the coupling of the first gauge group and the second gauge group, effectively it's like changing also at the same time. If you want to preserve an equal supersymmetry, you have to multiply the Z1 by G1 and the Z2 by G2. So that's kind of what I mean. All right, so I'm going to argue that there are some hidden symmetries in this problem.
So Costas, is that unique, that superpotential, the structure?
By n equals 2 supersymmetry. So
Okay.
Z2 orbifold and n equals 2 supersymmetry. Unique up to field redefinitions. You can. So if you want, you can absorb these couplings, let's say by rescaling Z1 and Z2, but then your kinetic terms are not going to be canonical. So if you want canonical kinetic terms, Z2 orbifold, n equals 2 supersymmetry, then this is pretty much unique. All right, so I'm going to claim that there are some hidden symmetries here, and I'm going to first work at the orbifold point. So that's G1 equals G2, and claim that already there is something more to see, and then I'll move to G1 not equal to G2. Okay, and I'm aware that I'm probably already kind of running out of time, so I'll but anything I kind of convince you of, I think is going to be. Okay, so the claim we're going to make, well, first of all, okay, let's see what are the symmetries in general. The symmetry that I'm going to be working on is the R symmetry, which acts on the state space, which basically you could think of as, so some matrix RAB, A goes from 1 to 4, that's our R symmetry, and that acts on states which are psi, which are made up of, you can think of as being made up of these fields. They've got a single field sector, there's only one X, a Y, a Z, and so on.
This is
What-
SU asymmetry, right?
Well, I'm talking about SU4. So this is before, this is at n equals 4 level.
Oh,
What happens when you go down to n equals 2? This, as you rightly claim, breaks down to an SU2 times an SU2. I'm focusing again only on subgroups of this, not the 31 points, times SU1. This you can go left, right, and R. This is the usual R symmetry. This is a somehow accidental symmetry that you get. You can see it here that the X and the Y appear in the same way. So there's an SU2 symmetry rotating those, but that's not generic. If you go to a Z3 orbifold, that's not there. But for this case, it is, yeah? So our claim is that, just to give the main idea, that's 10 equals 4. However, we claim that this is still there fully in the n equals 2 theory, as long as you replace the set of states by something that we call a path groupoid, which I will explain, and as long as you replace this R by something known as a Lie algebroid. Okay, in a compatible way. So let me just say a few words about what a groupoid is, and before I explain what the statement
What's the
is
U1
about.
R doing?
Sure.
What's the U1 doing here? In
The U1 is just a diagonal. We're not really worried about it. I mean, you can write. So you can write all of the generators. So usually we call these the generators 3, 4, meaning that if you look at R 3, 4 and R 4, 3, and then some diagonal bit, that's this SU2. If you do 1 and 2, so R1, 2, R2, 1, and something diagonal, like R1, 1 plus R2, 2, then you get this SU2, and there's a remainder. There's one more generator that you can write, which is some combination of 1, 1, 2, 2, 3, 3, 4, 4, which is non-trivial. So that's what remains. But this is not going to affect us very much, at least not at the level of this talk. Okay, so the claim is that a group, the SU4 group, has to become a groupoid. Or, okay, technically I'm at the level of the algebra, so it will be an algebroid. Let me explain first what I mean by the idea of, what is the original idea that we want to act, and then why we need the groupoids. The reason that the group is broken, the R symmetry is broken, is because in n equals 4, you could write this, work in the sector of x's and z's. You can write the sigma minus acting on x, that gives you a z. In this theory, the x is a bifundamental, the z is still an adjoint. So if you want to put these in a doublet, obviously this makes no sense if you're thinking in a standard algebraic language, because you are relating things which belong to different representations of the gauge group, right? Of the two gauge groups. But what we are going to claim is that this formula actually still makes sense if you expand your kind of understanding of symmetries to include groupoids and algebroids. Okay, so what is a groupoid? Let me start with the path groupoids, and then I'll explain the more general case. So what basically a groupoid is like a group where not all operations can be composed. Okay? So that means that you can, in a group, group is a set, okay, with some structure, but if you have some generators, you can always follow them by another generator, right? So you can act with sigma minus, and then you can act with sigma plus in a different subgroup and whatever. So the statement here is that for groupoids, you have to be more careful. Not all operations can be composed. So there is a bit of a definition here that I can give. So you can define by G0 a set of objects, by G1 a set of arrows between the objects, and there are some kind of what is known as structure maps, which are okay, there's a few of them, but the main ones are the source and the target. And what they mean is that if you take some objects, you can, so for instance, let's think of the path groupoid here. Now this is going to be this is not going to be our symmetry, this is going to be the vector space on which their symmetry acts, right? So our module, if you wish. and I'm claiming this is going to be a path groupoid. So obviously, if you want to define states, as I explained earlier, you need to start somewhere, you need to follow an arrow, and then, from here, you can only follow another arrow like this, maybe another arrow like this. So you cannot compose these arrows unless the endpoint of one arrow is the starting point of the other arrow. So in this language, which, has a bit of a categorical flavor, you think of your arrows as, so G is is an arrow, so G belongs here. And there is an element which is the source of the arrow and an element which is the target of the arrow. And in this simple case, you could say that if you call your G0, your objects to be 1 and 2, so that's gauge group 1, gauge group 2, or node 1, node 2, then obviously the source, let's say, of x12, that is 1, the target of x12 is 2, and you can do the same for all the maps, and you can prove all the structure constraints for the groupoid, that things are associative and all that. That is not our main point of, or the main structure we're interested in. This is very well known. People have been working about quivers and groupoids for many decades. What we are, our kind of, well, hopefully innovation, you could say, is that we're trying to make sense of formulas like these by thinking, okay, now this is an element of the path groupoid. This is also an element of the path groupoid. You can generalize this, I'll do it in a second, to more sites. But now we want to think of the generator of the R-symmetry group, in this case SU2 generator, as also an element of something which we're going to call a Lie algebroid. Now an algebroid is the same, has the same relation to the groupoid as the algebra has to the group. So it's basically the infinitesimal version of the operation. And you can think of, so if you want to think of the R-symmetry now.
Sorry, this
yes.
groupoid makes sense even for continuous groups. I mean, as you generalize this continuous groupoid.
Yes, yes. So that's what a Lie groupoid is. Yeah. So this is what I discussed here. That's of course discrete. That's the path groupoid. But now we want to go into the continuous thing. Not only that's generalized, but many ideas from groups like Noether's theorem and stuff also generalize to these Lie groupoids. We haven't explored that direction yet, but it's something we definitely want to. Okay, so here for the R-symmetry groupoid, or okay, let me call it a groupoid, but actually we're working with the algebroid. We have as our set of objects, we have the fields and so on. So basically, the maps of the path groupoid are the objects of the R-symmetry groupoid, and this G1 is the generators, which we now have to split into the generators that act on fields which have first gauge group 1 and fields which have first gauge group 2. So we basically need to split them. There's identity for first gauge group 1, sigma plus, minus for gauge group 1, sigma 3. This one is not a broken generator, this is an unbroken generator for gauge group 1 and 2, okay, and so on. So we just need to, that's all basically we need to do, and okay, I'm not going to give you all the details, but you can, from the paper, you can look at them in
Sorry, what was G0 and what is G1?
yeah, so for a groupoid, you need to define in this kind of more category kind of definition, the set of objects and the set of arrows. So for the R-symmetry groupoid, the set of objects are the fields, not necessarily only the fields of length 1, but all fields. So you could also have x1, 2, z2, that's also part of here. Okay, I'm just giving length 1, but it can be any length. And then G1 is the set of, just your generators, but we split them into the generators that preserve, so that act on fields whose first index is 1, and fields whose first index is 2. And they preserve that index, just like I wrote here. This is a convention. I could have made it so that we could have defined this action so that it gives you a Z2. Because it doesn't matter whether you choose, you're acting from the right or from the left, essentially. We just chose this convention. Okay, it's a breaking of the symmetry.
So all the parts of the bar groupoids are the objects of the big group, energy point.
Yeah, so that has an interesting structure of something like a 2-category or something, but okay, our focus has been on explicit computations and not so much on the abstract definitions of this. But okay, hopefully it's semi-clear what we want to achieve here. So we want to have a definition such that, if you look at the formula, then the source of sigma minus 1, this is now sigma minus 1, is x, and the target is z1. Okay? And you can do the same for all the generators of SU4. Some of them are unbroken, so the source and the target are in the same node. That's what unbroken means, that it takes you back to the same node. If it takes you a different node, then that is a broken generator. Naively broken, but now restored in this group weight.
So
This is all.
Sorry, sigma minus, it acts only on x12? It doesn't act on any other things?
Yeah, so we are working, yeah, so no, it will also act on, so this is a specific operator in SU4 language. This is for, I think it's R32. This will either take an x to a z, or it will take a z bar, the conjugate, to an x bar. So they act on both. But here I'm focusing just on the holomorphic.
But the holomorphic only that.
Yeah, in the holomorphic only that. I mean, this is sigma minus in this sector, right? In the xz sector. Then there is another sector, vy, z, and there's also an xz, xy sector, which is unbroken. Because the x's and the y's have the same dating, so this is an unbroken sector.
And how does it act on a composite part?
Okay, so that's actually where things become a little bit more concrete, because now we want to act not on single sites, but on spin change. And there, to make this, again, I'm kind of skipping, of course, some definitions and proofs. What we need to do, maybe first I need to remind you, how do I act on a product of states, say xx with sigma minus. In general, suppose I have two states, this is just from quantum mechanics. Well, this by itself makes no sense. You need to have a coproduct. Right? The coproduct is the operation which tells you how to distribute the action of a generator into two or more sites or copies of the vector space. What's a typical coproduct for any Lie algebra? It is 1 times sigma minus plus sigma minus times 1, which gives you, right? Which gives you xz plus zx, right? Because either you act on this, leaving the other one alone, or the other one. Right? So, is this a few more here? I think, okay, this is just how we normally, for a Lie algebra, how we act on multiple sites. Now it's kind of clear what's going to happen, right? So, if you want this formula to be true, then suppose you are here. So basically, you're taking xx, now I have an x1 to x1, and sigma minus, this part of sigma minus, is going to give you a z1. Obviously, you cannot follow that by x1 2, so by x1, as it was. So this has to change. And the correct statement will be that this is an x1. How do you achieve this? Well, you modify your coproduct by putting a factor gamma. Gamma is the Z2 operation, which takes any index to, so x1, 2, to x to 1, etc. So it basically just flips your, no, it just has Z2, which at the same time also takes kappa to 1 over kappa, if you are in the non-orbifold case. Here we're still at the orbifold case, but just for future reference, because I might not get there, it takes you for kappa to 1.
Sorry, there's no problem, right? Because if you took trace of xx as your original operator, then the indices don't match up after this group.
Precisely. So that was actually the main problem that we had to deal with in this work, because this is something that is technically part of a trace, it's closable. When you do this, this is an open, this is something which is not closable. But this actually has been encountered before many times anytime you're trying to apply quantum group symmetries in field theory. And the solution has always been, and that's what we always follow, to apply a symmetry trace prescription. So the idea is that whenever you think of something which is in a trace, first open it up. Then act with your quantum group generators. This is not a quantum group, but it's in a similar framework. Act on the open state that you get by cyclically opening it up, and then close it. This we cannot close, but obviously if you act twice, by the same logic, you get something which is closable. So you would need to act twice with your generator, with a broken generator, in order to get something that is closable. Okay? And you can say, okay, so basically that means that in the intermediate stages we're working with unphysical states, because they're not gauge traces. Is that a problem? Well, that was one of the main challenges we had and the main things we studied. And definitely for the orbifold case, where G1 equals G2, it turns out not to be a problem. Basically what I'm trying to argue here is that by acting twice with a broken generator, you can relate the spectrum, states in the spectrum of the theory for any length to some high straight state, and then lower, and get the correct states that you would expect. Okay?
So saying that delta sigma minus squared is an operator, but delta sigma minus is not.
So exactly. So if you double it, but we don't know how to do it in one go. We need to open up an intermediate stage.
So but define it by matrix elements, right? If you're taking physical states to physical states, you can just define an operator by matrix elements. So delta sigma minus squared is like a physical operator, you go delta sigma minus is not.
Yes, I think that's a good way of saying it. It's a little bit trickier when you're working with the kappa case, the non-orbifold case.
Oh, I see. Okay.
Because then, okay, I mean, you're probably right that we can do it that way, but it's easier for us to do it in 2 steps, because these now gain factors of kappa. Okay. So anyway,
what? I don't understand why you have to do it twice.
Sorry?
Closure that you're talking about, why do you have to do it twice?
So this, if you put gauge indices here, this you cannot make a trace here. Because let's say this has indices A of the first gauge group, B of the first gauge group, X has index of B1, but then it's a B2.
Compatible with the next also.
Yeah, but suppose this is all you have,
I see.
then this is not something you can make it no trace. Right? So you need to, you need to think of it as an open state that you're having. And that was the approach that we took. And in particular, in this approach, you can show that, let's say, if I take this potential, but as an open state, so take this potential I wrote earlier, which is still kind of here, but at G1 equals G2, and open it up cyclically. And you can act with all generators of SU4 and get 0. And you can also take the quartic terms. So that's the scalar potential. You can also act with all of SU4 and get 0. And of course, the kinetic terms as well and so on. So at the orbifold point where it's kind of trivial, more or less, with this prescription, to show that with a single action, not with, just with a single action, of course then it follows it for 2 actions, you get invariance. So this is our claim of the groupoid symmetry at the orbifold point. In short, this uses the planar limit. So when I'm saying this is technically not a true symmetry of the Lagrangian, even though I'm acting on the Lagrangian here, on this potential or in components in V, because we're assuming that the action preserves somehow, traces. If it was a truly non-planar action, it might not have done that. So we are using a hybrid approach, which has been used recently with some success by Bizert and collaborators as well, when they were trying to prove Yangian symmetry of N equals 4. And again, the Yangian is a quantum group, and it's to act on the Lagrangian. You have to act on the planar Lagrangian, because otherwise there's no Yangian. So they have some techniques very similar to ours to do that. Okay, any questions? So this is the first part, the orbifold point. Now, the second part, okay, I'll just very quickly say a couple of words. So far, what we showed is this groupoid symmetry, but now we need to go into the more complicated case where G1 and G2 are not the same. And that's what is, of course, most interesting, because practically everything about the orbifold point is known. We're not really gaining anything more. It's clear there has to be additional symmetry because it's integrable. Okay, so maybe this will help in finding a Yangian for the orbifold point, which hasn't been shown yet, but it's not so spectacular, I would say. But then, what we need to do here is twist. Okay, so something like a Driffield twist away from the orbifold point. And the guidance that we have about this comes from quantum planes. So maybe briefly, what is a quantum plane? A quantum plane, construction, mainly due to Manin originally, is when you take the coordinates of your space not to be commuting, something like this. And it's work that already dates back to, in the case in the context to work with Vishnu and Berenstein and Lee in around 2000 or so, which study the quantum plane structure of, let's say, marginal deformed theories. And that's what we're doing here. We're doing a marginal deformation. So maybe just to give one the feeling. So what we do is we take, let's say, an F term. So the F term of Y12 is X12, Z2, minus 1 over kappa, Z1, X12. And we find a twist, a Driffield type twist, which reproduces this quantum plane. And we do the same for all the other quantum planes that you have. So we look at all the F terms, we look at all the D terms. They look something like this, X bar minus X bar X plus, and so on. These are X12, X21. And we find corresponding twists. An example of such a twist is, okay, this is a different F, a curly F in the X sector, something like kappa to the minus S over 2 times kappa to the minus S over 2, where...
Sorry, why are you calling it a twist? What is being twisted here?
Yeah, I'm twisting the algebraic structure. So I'll just write two more formulas and then I think I'll stop. So here S is something which is 1 or minus 1 depending on the gauge group of the first index of what you're acting on is 1 or 2. And so for instance, if I act with this twist on let's say X12, Z2, then I look at this index, that's a 1, and look at this index, that's a 2. So I would put a factor of 1 over kappa for this one and a kappa for this one. Because the first index is a 1, so it's minus S over 2. So actually minus the half. Something like that. So for each product of fields you're acting on, at two sides, you just apply this twist and you get the same thing back, it's diagonal. But in this case, it leaves it the same. But if I was acting on Z1, X12, you see the first one is a 1, this is also a 1, so this becomes 1 over kappa. Is it clear, kind of, at least what this does? So I'm taking this, so I'm acting with this, on the first field I act with this, on the second field I act with the same thing. What is it twisting? It's twisting the coproduct. So we're writing, and this is very standard in quantum groups. So this is a quantum group that we're defining.
Are there any consistency conditions that this structure has to satisfy? When one talks about this quantum groups or something, there is this
associativity and stuff.
associativity, and then there is some other non-trivial condition, right?
I mean, yeah, so okay, we need some inverses called the antipode, and but there needs to be consistency. Okay, so there are a few consistency conditions, so I can mention them, but just let me write.
Sorry, one kappa is missing there, right? Kappa for the first term. Yeah, kappa. No, below.
No, this is one, because each of them gives you a square root of kappa. So see, it's
So
minus
there is
s
no
over
kappa
2.
multiplying the first term.
So here I'm saying f on this.
That is kappa times, right? You said 1, it's 1, 2.
It equals
Oh,
1 over kappa
I
because
see.
it's minus s over 2. So this is a 1 and a 1, but it gives you 1 over square root of kappa. What I'm twisting is the algebraic structure of the coproduct. So the formula is this. That's a formula by Drinfeld, which tells you when you twist your algebraic structure, how does the coproduct change? Actually, this is the more fundamental formula, the twist comes after. So if you take that coproduct that I had earlier at the orbifold point, which is 1 times sigma plus sigma times gamma, then you want to twist this. So you're multiplying by this f and this f minus 1. Okay. It's not totally obvious, of course, immediately how it works, but in this case it's actually quite simple. You can prove that this gamma does not commute with s. And actually it anti-commutes, so gamma s is minus s gamma. So that means that whenever you have a gamma in your undeformed coproduct at the orbifold point, when you twist, and this twist contains some s's, then some s's are going to be left over. And in particular, what happens is that you get 1 times s, sigma, plus sigma times gamma. That's the orbifold point, but now times a kappa to the s. And acting with this, so this is a new coproduct. About now 60% or more even of the paper has to do with how you take this from acting on 2 sides to 3 and 4 sides. Because we still want to act on the small potential and on the scalar potential.
But isn't the coproduct co-associated?
It is not co-associative, unfortunately.
Oh,
At least the way it's defined.
Some heap of algebra, not a real algebra.
Yeah, so it's a quasi-Hopf story.
Okay.
So we have a quasi-Hopf group point story. I don't want to go into that, so I'm not going to write anything more. But yes.
The twisting, is it some kind of introducing non-commutativity?
Yes. It's exactly doing something like this. So taking a commutative quantum plane, which was, okay, even take this, okay, the quantum plane has a minus, but take this and then you put a Q or somewhere, or a kappa, so it becomes non-commutative. Yeah, it's introducing non-commutativity. This makes sense also from a string theory perspective that there should be some non-commutativity because there are B fields that are turned on and vanishing cycles when you are turning on the marginal deformation. So also in the string theory standard, open string metric and so on, you expect to see some non-commutativity. So it's not something surprising in a sense, but working out the structure and needed some heuristics because we cannot directly go from 2 to 3 to 3 to 4. So the 2 sides is fine, but the other ones we had to make some educated guesses. In the end, those guesses, to save you, another 1 hour of discussion, they worked out and we were able to show, also for the kappa deformed case, that the planar action, in the sense I explained, is invariant under this twisted groupoid version of SU4. So our claim is that these deformed orbifold theories have the full set of generators of SU4, so the same as N equals 4. And that might explain various things, including planar equivalences and things like that, but it might also have further implications. Okay, hopefully something to do with integrability, but hopefully we can also use this to prove some word identities, relate operators between them. We took some baby steps. For instance, we looked at the BPS sector, and for the BPS sector, Abhijit and his collaborators have found some very nice formulas for how the factors of kappa appear in various, for any length and for any operators, and we can reproduce them on the nodes. So we are able to, we call this kappa symmetrization. I'm not sure if you used that name back then. But for the symmetrized states, for any length, we can reproduce the powers of kappa, starting from a highest weight state, and then acting with sigma minuses, and then getting for any state, you can get the correct factors. So we can reproduce aspects of the spectrum, Not only BPS, we also looked at non-BPS states. We looked at the 20 prime, which is BPS in the full sector, but also the 15, like various other states in SU4 that we were able to reproduce using our twists.
This is all loop version?
No, this is one loop. I mean, we're not aiming to do anything more. So this is basically this is classical, I would say. I mean, this is just the classical symmetries of the Lagrangian of the field that we are looking at. But of course, we're doing that using knowledge from the one-loop Hamiltonian. We don't know. I mean, it's a good question whether this structure will get deformed at higher loops or states. Anyway, so we are hopeful that there is more to the story. We have definitely not studied representation theory more generally. We just only looked at BPS, where we think everything is kind of clear. For non-BPS, only like 2 sites, and we have some initial stuff for 3 sites. Then things start getting a bit more messy. So it's not clear to us whether it's going to be helpful. For BPS, I think that it's a nice story. Okay, I think that's all I have to say.
I have 2 questions. One is about one of the last comments you made, because there is a classical story. Now, when I have quantum system of quantum group symmetry, typically the classical system has some sort of Poisson group symmetry, right? Poisson group symmetry.
Yes.
But
In that sense, yes.
But here you all have Poisson group itself, not a Poisson group or some Poisson group or whatever.
Yeah, so I don't mean classical in that sense, because Poisson-Lie is when you start thinking about the classical Baxter equation and taking a quantum system to the classical. I think that you would get that if you were to expand, write kappa as e to the h and expand. Then I would expect to get a some groupoid version of the classical Baxter equation, or the quasi-Hopf version of that. Okay. So it's something we have looked at, but we don't have anything very smart to say about it. So that is where you expect the Poisson-Lie structure. We are seem to be getting the full SU3 or the full SU4 as the. Okay, maybe I should correct the mistake I made here. Obviously, the potential is not environment in SU4. It's only in SU3. This is environment.
Second question I had was I'm trying to, from a broad level, is the main sort of ingredient that these delta sigma minus squared and other such physical operators actually relate z, z and xx and they're actually symmetric with the Hamiltonian?
Okay, yes. Well, we can show it for BPS, obviously, because these are states that have energy 0 for the Hamiltonian, and we can show that they're all related.
Oh, okay, I see.
For BPS. For non-BPS, so for states which are different representations and all that, it is clear, looking at the spectrum of the Hamiltonian, that there are splittings.
Okay.
So the same multiplet of n equals 4 splits into different states with different energy. Despite that, we are able to reproduce the wave functions, so the states themselves, even though these have different energy. So we're not claiming that the symmetry commutes with the Hamiltonian, but it seems that it's still useful for organizing the spectrum, even though in the spectrum you have states with different energy. Okay? This is not unusual for quantum groups. This is something that it's too much to expect, of course, that there's a whole degeneracy because of these symmetries, because we don't see it. The spectrum has been analyzed quite well, and it's clear that there are energy splittings, apart from the BPS states.
Certainly, you don't have quantum dimensional degenerate spaces.
I mean, the idea is that one day we'll be able to understand the difference, the energy splittings, through representation theory of this structure. We're not there yet.
One question.
So co-algebra is non-co-commutative.
Yeah, it's non-commutative. Yeah.
And then the algebra?
So the algebra, funnily enough, here is exactly the same. So we are able to show for our deformed product that, let's say, delta of RAB, delta of RCD satisfies the usual n equals 4 RCD minus delta C, B, R, B. So that's the usual SU4. So this is delta. Okay, and that's true also for the deformed. For when we say F, I mean the one with the kappa deformed case. Funnily enough, the actual algebra relations, the commutators, the quotation relations are the same as in the undeformed case. That's not normal. In normal quantum groups, you change the algebra and you change the coalgebra in a compatible way. But I think because this case is so simple, because this coproduct is basically just these powers of gamma, some Z2s, it ends up so that the algebra does not get modified. So just the coalgebra.
I just found out what these relations, the consistency relations, maybe they are not relevant here, but in the cases again people discuss these, they're called cell relations.
Yeah, no, we did not look at cell relations.
But they are part of consistency conditions that this structure should satisfy?
Yes, and we probably don't have them, I must admit, because the cell relations are part of associativity requirements, associativity constraints, like they're the generalization in a sense of Jacobi identities and all that. We might have some version, but not the precise relation that you would expect, because definitely we do not have associativity in the 3 and 4 sites. So we have to work in a non-associative setting, and that's why I'm saying about 60 or 70% of the paper was dealing with those cases and finding some heuristic but somehow motivated arguments as to why the cohort has to take a specific form.
You keep the same antipode when you twist?
We did not specifically look at the antipode in the twist. Yeah, that's something that needs to be done still. It seems this is very simple and invertible and all that, so I think it should be quite simple to write down antipodes, but we haven't done.
Okay, there are no further questions. Let's thank Costas Zoubos.